Have you ever wondered why some super smart AI, one that just crushes all its tests in a lab, can completely fall on its face out in the real world? Well, in this explainer, we're going to pull back the curtain and uncover the engineering secrets to building AI you can actually count on. Let's dive in.
Right? We hear about these incredible AI models all the time, but then they get deployed, and it's a totally different story. So what gives? Why do these brilliant models so often stumble when they finally meet the messy, unpredictable reality of our world? You know, the answer, and this might surprise you, it's usually not about having the latest, most complicated algorithm. It's about the foundation. Seriously, think about building AI like you're building a house. You could have the most beautiful blueprint in the world, but if you build that house on sand, well, you know what happens next.
So let's start right there, with that foundation that no one really sees. For any AI, that foundation is one thing, and one thing only, the data it learns from.
This quote from the research just nails it. Bad data doesn't just make your AI a little bit worse, it puts a hard limit, a ceiling on how good it can ever possibly be. You literally cannot build a world-class model on garbage data. It's just not possible. So what exactly makes data bad? Well, let's meet the usual suspects. You've got things like noisy labels. That's like trying to teach a kid what a cat is, but half the time you're pointing at a dog. You've got missing data because a sensor failed, or maybe sensor drift, where a camera's color balance slowly changes over months. Or maybe you have imbalanced classes, where you've got a million pictures of healthy machine parts and only 10 of a failing one. Any one of these villains can totally poison your dataset and teach your AI all the wrong lessons. Okay, so once you have that foundational material, your data, you can't just start building. Nope. You've got to prep it first. Just like a carpenter has to measure, cut, and sand their lumber, AI engineers have to turn that messy, raw data into clean, high-octane fuel for the model.
This whole prep stage is called pre-processing, and it usually follows these three key steps. First, you clean the data. You find and deal with all those errors and missing spots. Second, you normalize it, which sounds technical but is absolutely critical. And third, you select the best features, which is all about helping the model focus on what's important and tune out the distracting noise.
So why is normalization such a huge deal? Just look at this. On the left, you've got raw data. That pressure value is massive compared to everything else, right? Without normalization, an AI would look at that and think, whoa, pressure must be thousands of times more important than temperature just because the number is bigger. By scaling everything to a common range, like you see on the right, we put all the features on a level playing field, letting the AI judge them by what they actually mean. Okay, our foundation is set, our materials are prepped. Now it is time to actually build and test this house. This is the training phase. It's where the AI model actually learns from all that clean data. But, and this is a big but, we have to make sure it learns the right way, without any cheating. And to make sure there's no cheating, we split our precious data into 3 different piles. The biggest chunk, the training set, is the textbook. It's what the model actually studies. The validation set is like a series of practice quizzes along the way to tune how it's learning. And finally, the testing set. That is the final exam. It is brand new data the model has never ever seen before, and it gives us the honest-to-goodness truth about how well it actually learned.
Now, one of the absolute worst sins you can commit in this process is something called temporal leakage. This is a huge problem with data over time, like stock prices. It's when information from the future accidentally contaminates your training data. It's literally the same as giving a student the answer key before the test. The model will look like a total genius in the lab, but it's completely worthless in the real world because it can't actually see the future.
This brings us to one of the biggest challenges in all of AI, what I call the Goldilocks dilemma. You don't want a model that's too simple, you don't want one that's too complex, you need to find the one that is just right.
So on one side, you've got underfitting. In our house analogy, this is like building a tiny, flimsy shack. It's so basic, it completely missed the point. It'll get blown over by the slightest breeze. On the other extreme, you have overfitting. This is like building an insanely complicated mansion that's perfectly designed for one very specific sunny Tuesday. It hasn't learned the general rules of building, it's just memorized every single detail of the training data, including all the noise. The second the weather changes, the whole thing falls apart.
So how do engineers find that just right sweet spot? Well, they have a whole toolkit of techniques called regularization. This includes stuff like data augmentation, where you create new training data just by, say, flipping or rotating your existing images. Another one is dropout, which is kind of brilliant. It's like you force the AI to study, but you randomly make some of its brain cells take the day off. This forces the rest of the model to learn more robustly instead of relying on any one part. All these tools stop the model from just memorizing and force it to actually learn.
But what if you don't have a mountain of data to start with? This is a really common problem, and this is where engineers have learned to work smarter, not harder. Instead of building our entire house from scratch with raw lumber, they use high-tech, prefabricated parts.
And the most powerful of these strategies is called transfer learning. The idea is pure genius. You take a massive model that a big tech company has already trained on millions of images. That model already knows what edges and textures and shapes look like. You just take that pre-built intelligence and fine-tune it for your specific problem. It's a huge shortcut, and honestly, it's often the most practical way to get incredible results without needing a giant dataset.
And there are other smart techniques too. There's few-shot learning, where you try to train a model with just a handful of examples. And then there's continuous learning, which is so important for the real world. This lets a model, say one that's predicting fashion trends, constantly get updated with new data, so it can adapt as the world changes and never goes out of style.
So here's the bottom line. Creating AI that actually works isn't magic. It's not some unknowable black box. It is a process of disciplined, step-by-step engineering. It's all about laying a solid data foundation, carefully prepping your materials, testing everything honestly, and using the right tools for the job.
And that leaves us with one final, really important thought. We've seen just how much depends on that unseen foundation. So as AI gets built into everything, our cars, our hospitals, you name it, who's responsible for making sure that foundation is solid? Whose job is it to inspect the work? That's the big question we all need to start asking.